right, chemistry, let's take a look at our video lecture for Chapter 10, Section 3. We're looking at the gas laws. In this first part of our video lecture for this section, I want you to be able to use the kinetic molecular theory to explain the relationships between gas volume, temperature, and pressure. I want you to be able to use Boyle's Law to calculate volume pressure changes at constant temperature. And then I want you to use Charles's law to calculate volume temperature changes at constant pressure. Now that probably doesn't make a lot of sense to you at all, but what we're going to be doing is we're going to be introducing some new, small, very simple equations to help you make those calculations. Now, so far in this chapter, we've talked about various characteristic properties of gases, things like compressibility, things like fluidity, expansion, and those are truly characteristic properties of gases. Okay, they define what it means to be a gas. However, they're not easily measurable. So when it comes to the measurable, like in a lab, in a container, I can take temperature measurements very, very easily. There are 4 properties that are easily measurable and that we are going to use to solve the equations that we are going to look at in this section. First up is pressure, represented by a capital P. It is the pressure exerted by the gas. Remember, all these little individual gas particles are zooming around their container, and when they strike the container wall, right, that collision is putting kinetic energy into that container wall. It's exerting force, and that force is pressure. There's pressure on the container wall. Then we have volume, represented by a capital V. It is the total volume occupied by that gas. We have capital T, which is going to be the temperature in kelvins of that gas. And yes, that's kelvins is a temperature scale, and we do not say degrees Kelvin. Right? In the same way that we say degrees Celsius or degrees Fahrenheit, we simply say 273 kelvins. And then lowercase n represents the number of moles of gas. Remember, we're talking about moles. Moles represents an amount of a substance. It just so happens that in this particular instance, we're talking about moles of a gas. So keep that in mind. When the number of moles increases, the amount of gas increases. So let's start with Boyle's Law. Boyle's Law states that as volume decreases, the concentration and therefore the pressure increases. Now imagine, go back to imagining gas in your mind in a container. There are a certain number of gas particles in that container, and if we decrease the volume, we're decreasing the amount of time it takes for those gas particles to move across the container and strike the container wall. Because it's a smaller container, there's less distance between the walls of the container. And so we're having more collisions with the container wall. And more collisions means more pressure. This inverse relationship, which if you imagine it with me as we go along, it's pretty easy to get your head wrapped around it. But this inverse, remember inverse means as one goes up, the other goes down, or as one goes down, the other one goes up. Right? As volume decreases, pressure increases. This inverse relationship between pressure and volume is known as Boyle's Law. Again, Boyle's Law states that for a fixed amount of gas, right, we're not changing the amount of gas present at all, and we're not changing the temperature at all. The volume of the gas will increase as the pressure decreases, and the volume of the gas will decrease as the pressure increases. Again, inverse relationship. So we can represent Boyle's Law very, very well using the cylinder of a gas-powered motor. We have some gas particles in a cylinder over here on the left, and then the piston compresses that gas. Right, the same amount of gas is present, the same temperature throughout, but we're decreasing the volume. We see that each of these molecules that were present before, each one of these molecules has a much shorter distance to travel in order to collide with another wall of this container. So we're having more collisions, therefore more pressure. Now mathematically, we represent Boyle's Law as PV equals K, which means the pressure multiplied by the volume is a constant. As long as the temperature is the same, right? We're not changing the temperature. We're not changing the amount of gas, right? As long as those two things stay the same, no matter how we change pressure or how we change volume, because of the inverse relationship, the other value will change to offset that change. So if P gets really, really big, V will get very, very small, so that when they're multiplied together, they're a constant. It's the same value no matter what the change is. We can calculate changes in pressure or changes in volume by rearranging this equation to look like this. P1V1 equals P2V2. If we have an initial situation over here and we change the pressure, right? So we know what the pressure is. We can calculate the volume by simply rearranging this algebraically and solving for V2.
Pressure is caused by the collisions of gas particles with the side of the container. With a large volume, the particles do not collide with the sides of the container very often, and the pressure is relatively low. When the volume decreases, the particles of the gas collide with the sides of the container more often. With more collisions, the pressure increases. Boyle's law states that the volume of a fixed mass of gas varies inversely with pressure at constant temperature. In other words, the smaller the volume, the higher the pressure. The pressure of a gas times its volume is a constant.
Now, according to that relationship, that inverse relationship, we'll see, as is represented by this graph, we don't see a straight line. Okay? We see a curve. Okay? We see a curve. And this is going to approach 0 but never reach 0. Okay? It's asymptotal. There's going to be an asymptote over here. This is a pressure to volume graph showing an inverse relationship. It says as pressure increases, volume decreases, right? So as we go further to the right on the x-axis, which is pressure, we see that the value for volume gets lower and lower and lower and lower. Now, as pressure goes down, right, if we move to the left on the pressure scale, the x-axis, we see that volume increases, right? That's the inverse relationship. Now let's get a sample problem in. A given sample of gas occupies 523 milliliters, that's a volume, at 1.00 atmospheres of pressure. The pressure is increased from 1 to 1.97 atmospheres of pressure, while the temperature remains the same. Okay, so that's our clue that we get to use Boyle's law. What is the new volume of the gas? So this is what we know, right? We know P1, we know P2, we know V1. We need to solve for V2. So we're going to rearrange this equation because we have values for the other three terms. And so once we algebraically rearrange this equation, we have V2 is equal to 1 atmosphere multiplied by 523 milliliters divided by 1.97 atmospheres. Now look what's going to happen with our units. We have an atmospheres on a numerator and atmospheres on a denominator, so those will cancel. Is there anything to cancel out this volume? Do we see milliliters anywhere else? No. So milliliters as a unit will remain. And so when we plug and chug these numbers, we'll get 265, and the units will be milliliters, which makes sense because this is volume. It's V. Volume is represented by liters. This is milliliters. If we solve for this and we had atmospheres as a unit, or we had atmospheres divided by milliliters or the other way around, we would know that something's wrong because we're trying to solve for a volume. Our units need to be volumes. Now, pressure and volume are not the only relationships we're going to look at here. Temperature and volume relationships. Heating a gas makes it expand, and cooling a gas makes it contract. I think you guys know this already. Hot air rises, cool air falls, it descends. In 1787, the French physicist Jacques Charles discovered that a gas's volume is directly proportional. Yeah, that means when one changes, the other one changes in the same way, right? The change in the same way is directly proportional to the temperature on the Kelvin scale if the pressure remains the same. If the pressure remains the same, so the pressure is not changing. So this direct relationship between temperature and volume is known as Charles' Law. Now again, you guys already understand this idea naturally with the idea of, cool air and warm air. That is defined as Charles' Law because Charles was, the first guy to describe this and get that published. So Charles' Law states that for a fixed amount of a gas at a constant pressure, the volume of the gas increases as the temperature of the gas increases, and the volume of the gas decreases as the temperature of the gas decreases, right? When one changes, the other one changes in the same way. Now, the kinetic molecular theory states that gas particles move faster on average, okay, not every single individual one, but on average, they'll move faster at higher temperatures, causing them to hit the walls of their container walls with of the container with more force, right? If we're not changing, the pressure, we're changing the speed, the velocity at which these individual gas particles are striking the container wall. Greater speed, greater impact, greater force. So repeated strong collisions cause the volume of a flexible container like a balloon to increase, right? Because the volume is not set here. If we have a flexible container, and by the way, be prepared to look for that term within a question so that you can know if it's a fixed volume or a flexible volume, whether or not the volume can change or not. So gas volume will decrease when the gas is cooled because the lower kinetic energy of the gas particles at the lower temperature. They're moving more slowly, so when they strike the container wall, they will not strike with nearly as much force. So if the absolute temperature is reduced by half, then the average kinetic energy is reduced by half. Because if you remember from sections 1 and 2, kinetic energy is proportional to temperature. So if the kinetic energy is reduced by half, the particles will strike the walls of that container with half the energy that they did at that higher temperature. Now in that case, the volume of the gas would be reduced by half compared to the original volume, again, as long as the pressure is remaining the same.
Charles's law states that the volume of a fixed mass of gas at constant pressure varies directly with Kelvin temperature. Liquid nitrogen is very cold at 78 kelvins. When a balloon is placed in liquid nitrogen, the balloon shrinks. As the temperature decreases, the volume also decreases. When the balloon is removed from liquid nitrogen, the balloon returns to its original volume as the air warms the balloon to its original temperature.
This direct relationship between volume and temperature can be shown in a graph in which volume temperature data, as long as it's graphed on the Kelvin scale, right? We do not want to use degrees Celsius. We do not want to use degrees Fahrenheit. We want to use kelvins. If you read the line in the graph all the way down to 0 Kelvin, it looks like the gas's volume becomes 0. However, before this temperature would be reached, the gas would become a liquid and then freeze to become a solid, which will definitely have a certain volume. So that's just a kind of interesting quirk about this graph. But if we follow this line all the way down to the origin, it seems like, oh, okay, when we're at absolute 0, right, 0 Kelvin, there'll be no volume. That's not exactly the case because as these gas particles are shoved closer and closer together because of the small volume, they'll start interacting with one another because of their intermolecular forces, and they'll become a liquid, then become a solid, and that will take up some amount of space. But remember, this temperature is always kelvins. The other thing I want to point out, remember this is a direct relationship, and it forms a straight line. The inverse relationship created a curve, right? It created a curve. This is a straight line because it is a direct relationship. Now, when we're going to be doing calculations with Charles' Law, we're going to be using, again, a very simple equation. We have the relationship between volume and temperature as direct, right? When we carry out this division function, we will always have a constant because when one changes, the other will change in the exact same way, so the product will be the same. Now, again, in the same way we had P1 times V1 equals P2 times V2, if all the other conditions are held the same, we can calculate volume temperature data with the same strategy. V1 over T1 is equal to V2 over T2. Again, we can simply rearrange this equation to solve for whichever term we need.
For a gas maintained at constant pressure, the ratio of the volume of the gas to its absolute temperature is a constant.
Again, one more look at this direct relationship. Straight line. Straight line on the graph means direct relationship. Curve means inverse relationship. Let's take a look at a sample problem. If a balloon is inflated to 665 milliliters at 27 degrees Celsius and it is immersed in dry ice, which was coming in at minus 78.5 degrees Celsius, what is its volume, assuming the pressure remains constant? So let's use Charles' Law here. All right, let's see what we know. We know the initial volume, we know the initial temperature, we know the final temperature, we just need the final volume. Now, first off, these temperatures are in degrees Celsius, and that should stick out to you. I've been saying use kelvins, use kelvins, use kelvins, and these are not kelvins. How do we turn a degree Celsius temperature into a Kelvin? We simply add 273 to it. 1 degree Celsius is the same thing as a Kelvin. They just don't start at the same point, right? They start 273 away from one another. So it's actually kind of simple. If I give you a degree Celsius, you simply add 273 to it. So 27 degrees Celsius is actually 300 Kelvin. And minus 78.5 degrees Celsius, again, add 273 to it, is 194.5 kelvins. So now we have the correct unit for the temperature to stick into this equation. And now as we rearrange to solve for V2, we have two temperatures, both in kelvins, and they will cancel out. Now as they cancel out, we can plug and chug the rest of the numbers, but we still have this milliliter present, this volume present. And that makes sense, right? Because we're solving for volume, we need our units to be a volume. All right, guys, we're going to cut it off there. We'll pick it up next time we meet. I will see you next period.